So we've looked at the theory behind the scalar triple product. What I'm going to do here, I've got a couple of questions for you. I want you to read the questions, pause the video, have a crack at them, and then come back and check your answers with what I'm going to show you here. Here you go. So I've got three questions for you. First, I'm just telling you to calculate a triple scalar product. Second is applying it to a parallelepiped of your own, which I'm defining for you. And the third one is thinking about using some of the characteristics we talked about earlier when it comes to the triple scalar product. So pause the video and have a ping at them. So first one, I want to find A dot B cross C when I've got these three vectors here. So for this one here, start off the way that we normally would, write out what we're finding, A dot B cross C, and then stick it in our big matrix. So for this, I'm going to have 1, 4, 1. Watch out for the B. I've no J component, so I've got 1, 0, 2. Watch for when they put that in a question. And then I've got 3, negative 2, 1 for my C vector. I'm going to put my plus, minus, plus on the top, and then do as I normally would, split it into our wee matrices, calculate determinants, bash on. So I've got 1, then got 0, 2, negative 2, 1, take away 4, I've then got 1, 2, 3, and 1 there. I've then got plus 1, my wee determinant here, 1, 0, 3, negative 2. So do each of these and then see what we get. So this first one, I've got 1 times, well, 0 times 1 is 0, take away negative 4, so I've got 4. I've then got minus 4 times 1 times 1 is 1, take away 3 2's, so 1 take away 3 2's is minus 5 because it's 1 take away 6. I've then got plus 1 times this, so I've got negative 2 take away 0 times negative 2. Multiply all these out, I get 4 plus 20 minus 2, so I get 22 cubic units. So there you go, that's a triple scalar product of those vectors. Second question was finding the volume of the parallelepiped defined by these edges here. So again, this should just jump straight back to looking at the triple scalar product when you've got a three-dimensional parallelepiped with its edges defined by vectors in different planes. So straight away, jump to your A dot B cross C. So again, write it out as a matrix. So I've got negative 1, 4, 4. There's my B vector, 3, negative 2, 3. And then my C vector, 4. Again, no J component, so 0, and then 1. Put my plus, minus, plus at the top, and I'm ready to jump in with both feet. So I've got negative 1 times my wee matrix of negative 2, 3, 0, 1. I've then got take away 4 times the matrix made up of 3, 3, 4, and 1. And then plus 4 times a matrix made up of 3, negative 2, 4, and 0. Do each of these, see what you get at the end. So I've got negative 1 times negative 2, take away 0, so negative 1 times negative 2. I've then got minus 4 times, well, 3 ones, that's 3, take away 4, 3, so I've got 3 minus 12, so that's minus 9. I've then got plus 4 times 3 times 0 is 0, 4 times negative 2 is negative 8, so 0 minus minus 8. I've got 4 times 8 there. So, working each of these through, negative 1 times negative 2, I get 2. I've got negative 4 times negative 9, two negatives make up positive, so I've then got plus 36. I've then got 4 8s, which is plus 32. Add them together, and I end up getting 70. So I get 70 cubic units for that parallelepiped given there. Last one, show the position vectors for the point 1, 2, 3, 4, negative 1, 2, and 2, negative 5, negative 4. lie in the same plane. Now this is thinking back to some of the characteristics of a triple scalar product, specifically the one where we know that we take our triple scalar product. So if we've got A dot bracket B cross C, and if we get an answer of 0, we know that they lie in the same plane. So let's do that now. So position vectors, let's call A as 1, 2, 3. Let's call B 4, negative 1 and 2. Let's call C our final one, which is 2, negative 5, negative 4. Plug them in the matrix we know for a triple scalar product. So we've got 1, 2, 3, 4, negative 1, 2, 2, negative 5, negative 4, plus, minus, plus, and then bash through the process. So we've got 1 times our wee matrix with negative 1, 2, negative 5, negative 4, minus 2 times our next wee matrix of 4, 2, 2, negative 4, then plus 3 times our final wee matrix of 4, negative 1, 2, negative 5. Calculate all of this, stick it all together, and we hope our answer is 0. If that's the case, they're all in the same plane. So we've got 1 times, well, negative 1 times negative 4 is 4, negative 5 times 2 is negative 10, so I've got 4 minus minus 10, add them together, and I get 14. I've then got minus 2 times, well, 4 times negative 4 is negative 16, 2 2s are 4, negative 16 minus 4 is negative 20. I've then got plus 3 times 4 times negative 5 is negative 20, 2 times negative 1 is negative 2, so I've got negative 20 minus minus 2, so negative 20 plus 2, I've got negative 18. So what that then gives me is 1 times 14, well, 14 funnily enough. Negative 2 times negative 20 is plus 40. I've then got 3 times negative 18, so 3 times negative 18 is going to give me minus 54. 14 plus 40 is 54. Take away 54. Funnily enough, our answer is 0. So we've got an answer of 0 there. So our triple scalar product A dot bracket B cross C is equal to 0. What that means is they all lie in the same plane. So we've just used one of the properties we discussed in the previous video to prove what it was asking us to do. Make sure you go back and look at all those properties and remember them. You're expected to be able to recall them straight off the top of your head and be able to apply them in scenarios like this to questions of this sort of format so that you can just jump straight away and get them going.